$120 billion is the staggering annual revenue generated by the global bearing industry, as it produces tens of billions of individual units. These components function as the essential mechanical heart behind almost every movement in the modern world, from the rotation of a car wheel to the high-speed turbines of a jet engine. Why is such a massive volume of production necessary for a component that often remains invisible? While they seem simple, bearings are the primary defense against friction, stabilizing motion and ensuring that machines do not grind to a halt under intense mechanical stress. But this is just the beginning. The equipment gradually shapes these parts to possess extreme hardness and a high degree of wear resistance, turning them into a silent foundation for global infrastructure. It only looks obvious that a bearing should be durable, but in reality, its true value is found in a manufacturing sequence governed by absolute precision. One can notice how the raw alloy steel undergoes a series of transformations, including specialized heat treatment and precision grinding to achieve a state of near-perfect roundness. This ensures that every single rotation remains smooth and reliable over many years of continuous operation. The process is only gaining momentum. 120 billion units represent a product landscape that is among the most diverse in the entire engineering sector. Some bearings are manufactured to be small enough to rest on a human fingertip, appearing almost weightless. It gets more complex further on. At the other end of the spectrum, industrial versions can exceed 10 feet in diameter and reach weights of tens of tons. These massive structures are designed to support the immense blades of wind turbines or the heavy rotating drums of mining equipment. It is visible how these monumental components are engineered to neutralize friction while maintaining stability under loads that would crush ordinary materials. At first glance, the manufacturing of such different sizes might seem disconnected, but in reality, they all share a singular industrial chain. This complex sequence guides the material from its initial raw input through to the final stages of ultra-precision machining. One can notice the transition to the next level as the metal begins its physical metamorphosis. The narrative of every steel bearing, regardless of its final size or application, begins deep within the sourcing of the specialized alloys required for such performance. The material leaves the initial conceptual phase, transitioning into a calm stage of preparation for the heat and pressure of the factory floor. Tens of square miles of iron oxide deposits stretching across the earth represent the starting point for every steel bearing in existence. Why is mining conducted at such a massive scale? One might assume that iron is easily accessible, but these deposits lie hidden beneath a seemingly lifeless surface in shades of deep red, brown, and gray. These mineral reserves formed over millions of years and now wait for modern technology to awaken them. Geological engineers initiate the process. They survey the terrain and drill deep boreholes dozens of feet into the crust with absolute precision. The workers load these openings with a mixture of ammonium nitrate and diesel fuel to serve as industrial explosives. One can notice how the drilling rigs move methodically across the site. But this is just the beginning. The explosive charge detonates with millisecond precision to shatter thousands of cubic yards of rock. It takes the energy equivalent of several tons of trinitrotoluene to expose the rich ore buried underneath the waste material. It is visible how the ground buckles before a localized cloud of dust slowly settles over the site. At first glance, a quarry blast is chaotic destruction, but in reality, it is a calculation where over 1,000 tons of explosives are utilized every month. Everything only gets more complicated as the transition to the next level begins. Gigantic hydraulic excavators move into the blast zone. These machines feature buckets capable of lifting up to 40 tons of raw material in a single motion. They swing with a steady hiss of hydraulics to load the ore onto ultra-heavy dump trucks. These transport vehicles weigh between 200 and 300 tons and possess wheels that dwarf an average person. The equipment gradually fills the quarry with the sound of heavy engines as hundreds of controlled blasts free millions of tons of ore over time. Because the demand for steel is constant, Australia, Brazil, and Russia supply hundreds of millions of tons of this raw material to mills globally every year. This ensures that the production chain never stalls. Therefore, every transport cycle is precisely coordinated to maintain the flow of iron. The process is only gaining momentum. Every shovel load and every movement of the conveyor contributes to the transformation of the earth into metal. The camera glides along the massive ridges of the open pit mine where the entire operation unfolds like a colossal machine moving in a perfect repetitive rhythm. Boulders split with a crack as they are moved, and the material begins its long journey toward becoming the high-strength steel required for industrial bearings. The material is ready to move to the next processing phase without haste. Tens of tons is the weight of the massive steel rollers that first meet the raw iron ore as it arrives at the processing plant. These high-capacity crushers exert immense mechanical pressure to break down the rugged rocks into manageable fragments. But why is the ore subjected to such intense crushing and subsequent grinding in rotating ball mills? This sequence ensures the maximum release of iron from the surrounding rock by drastically increasing the surface area of the material. Only through this level of refinement can the separation stage reach peak efficiency. The process is only gaining momentum. One can notice how the ore is transformed into a fine, uniform powder that is perfectly suited for the next phase of refining. At first glance, this powder seems ready, but in reality, it must undergo flotation to remove lingering impurities. The powdered ore is mixed with water to form a thick, heavy slurry before being fed into enormous flotation tanks. Transition to the next level. Carefully measured surface active chemicals are introduced into the tanks to alter the physical properties of the particles. Because of these additives, the iron-bearing grains become hydrophobic, while silica and clay remain hydrophilic. One can notice how compressed air is blown through the bottom of the tanks, creating millions of tiny bubbles. These bubbles cling to the iron particles and lift them toward the surface in a continuous ascent. Everything only gets more complicated. Layer after layer of reddish-gray froth, rich in iron, is skimmed off the top by automated collectors. This cycle repeats multiple times until the specific desired purity is reached. It is visible how the waste rock and other impurities sink to the bottom to be completely removed from the chain. The result is an iron concentrate containing between 65 and 67% iron. The material is now ready to enter the metallurgical phase. After leaving the flotation tanks, the iron-rich slurry is directed into a specialized filtration and dewatering system. The suspension passes through vacuum filters, which may be of the rotary drum or disc type, where pressure differentials draw out the liquid. One can notice the fine ore particles remaining as a moist cake on the filter surface. This stage significantly reduces the moisture content to ensure ideal conditions for pelletizing. It gets more complex further on. From the filtration tanks, the concentrate is collected as a fine, dry powder with a distinct reddish-brown color. However, in this loose state, the material is too powdery to be fed directly into a furnace. To solve this, the powder is mixed with a small amount of water and binding agents before entering enormous inclined pelletizing discs. As the discs rotate steadily, the fine particles begin to cling and cluster together through centrifugal force. Millions of damp iron ore pellets gradually take shape as they roll across the surface. By the time they fall from the discs, they are round, smooth, and possess the exact moisture content required for firing. But this is just the beginning. The pellets are then fed from a traveling grate into a rotary kiln. This massive steel cylinder stretches dozens of feet in length and is set at a slight incline while rotating slowly. Inside the chamber, the temperature is maintained strictly between 2,190 and 2,460 degrees Fahrenheit. As the kiln drum turns, the pellets roll and tumble through a constant stream of high-heat gases. It is visible how they are baked evenly from the core outward to ensure structural integrity. Impurities are burned away during this thermal treatment while the iron particles fuse together. This creates a solid, dense, and uniform internal structure within every sphere. By the time the pellets exit the kiln, they have reached the mandatory hardness and density for the smelting phase. The process concludes this phase, opening the road to the formation of the steel that will eventually become colossal anchor chains. 3,600 degrees Fahrenheit is the temperature reached by the superheated air injected into the base of the blast furnace. Why is such extreme heat necessary for the transformation of raw materials? This intense thermal energy triggers a chemical chain reaction within the towering structure. It seems simple to just melt the rock, but in reality, the furnace must separate the oxygen from the iron ore to create metal. One can notice how the coke ignites, generating carbon monoxide that strips the oxygen away, leaving behind a stream of liquid pig iron. But this is just the beginning. Everything only gets more complicated as the materials interact. Layers of pelletized iron ore and red-hot coke from the ovens are stacked inside the steel structure that rises hundreds of feet into the air. Limestone is added to the mixture to act as a purifying agent. The process is only gaining momentum. As the air blast forces its way upward, the molten iron descends to the hearth, glowing bright red. It is visible how the impurities merge with the limestone, forming a layer of slag that floats like a protective crust on top of the liquid metal. But such industrial power comes at a structural cost to the environment. The blast furnace remains one of the largest sources of industrial emissions on the planet. Enormous volumes of carbon dioxide, fine particulate dust, and toxic gases are discharged during the reduction phase. Therefore, while it serves as the beating heart of the steel industry, it presents a significant ecological challenge. The process does not end at this stage. 100 tons or more of this molten pig iron are then transferred into the basic oxygen furnace. Inside this massive vessel lined with heat-resistant refractory bricks, the iron undergoes a violent refinement. A long lance descends from above, blasting pure oxygen at supersonic speed directly onto the surface of the melt. The camera glides along the rim as jets of flame and spark shoot high above the furnace mouth during the reaction. Under this thermal and chemical pressure, the carbon content drops rapidly. This transforms the brittle pig iron into refined molten steel that is stronger and more ductile. The metal lays in an even layer as it moves toward the continuous casting system. It flows into water-cooled molds where the liquid begins to solidify into its very first solid forms. These may be square bars, wide slabs, or rectangular blooms. At first glance, these shapes look finished, but in reality, they are merely the raw billets for the next phase. The shaping journey begins. Thick slabs and blooms enter the reheating furnace before passing through massive rolling mills. The equipment gradually applies immense pressure using rollers that weigh tens of tons each. It is visible how the metal stretches and thins under the mechanical force. Thick slabs are flattened into thin steel sheets, while blooms are rolled into coiled strips and square billets are drawn out into long bars. With every thunderous turn of the rollers, the steel acquires the specific dimensions required for skyscrapers, bridges, or automobile frames. The metal is ready for casting, where it will take shape. Thus, the steel reaches the standard ready for the further stage. 100 high-carbon steel bars arrive at the fabrication facility from the metallurgical plant to begin a rigorous verification cycle. Every unit undergoes a thorough inspection where technicians confirm the specific steel grade, precise diameter, and surface hardness before the material is cleared for the cutting line. These solid round bars are typically composed of a specialized high-carbon alloy integrated with chromium. This specific chemical composition is selected for its superior wear resistance and structural stability, which are the two primary requirements for industrial bearing production. It gets more complex further on. Why must the steel grade be verified multiple times before any physical processing begins? A single error in material identification could compromise the structural integrity of the entire production batch. This validation ensures that every centimeter of the alloy will react predictably to the intense heat and pressure of the upcoming forging stages. Automated hydraulic cutting machines operate in a continuous cycle as the steel bars are moved into position. One can notice how laser sensors calibrate the exact placement of the metal before the heavy blade descends with a rhythmic mechanical strike. Each cut produces a short cylindrical blank with a length calculated down to the millimeter. These blanks serve as the geometric foundation for components that will eventually be forged and machined into high-precision rings or balls. The process is only gaining momentum. Dimensional accuracy is checked immediately following the cutting stage. Every blank is measured for mass uniformity to ensure complete consistency across the production line, as precision engineering allows for zero compromise in weight distribution. The equipment gradually moves the validated pieces along roller conveyors toward a primary heating station. One can notice how the cylindrical steel blocks transition from a cold, matte finish to a state prepared for thermal processing. This represents a massive chain of transformation that spans from iron ore extracted from the deep earth to refined steel blocks approaching the micron level of machining. Transition to the next level. Once the material is cut into uniform steel blanks, it undergoes a phase of controlled cooling. This specific thermal deceleration stabilizes the internal crystalline structure of the high-carbon alloy and relieves residual mechanical stress. It seems simple at first glance, but in reality, this stabilization prevents the metal from warping during subsequent machining. The blanks are eventually fed into the high-heat environment of the primary furnace. Within this tightly regulated chamber, the steel is brought to a specific temperature where it becomes significantly more ductile. It is visible how the metal softens, preparing to withstand the immense compressive forces required for industrial forming. This state of ductility is essential before the blanks are subjected to the automated ring rolling system. Everything only gets more more complicated. Immense compressive force is applied as the heated steel is bent and closed into a seamless ring. This mechanical action creates the foundational structure for both the inner and outer bearing races simultaneously. The forming process occurs at high speed, yet it remains under strict digital control to maintain perfect concentricity and minimize any geometric deviation from the central axis. One can notice how excess material along the edges is trimmed away immediately by automated cutters to ensure a clean and balanced profile. This prevents imbalances that could lead to vibration in the final mechanical system, and this is not the limit. The steel rings enter a mandatory heat treatment cycle to finalize their physical properties. The metal is heated to a high temperature and then cooled at a precisely calculated rate, a process known as quenching and tempering, which increases surface hardness while improving long-term resistance to friction. As a result, each individual ring achieves the necessary tensile strength and a stable internal grain structure. This creates the critical foundation for the final precision machining stages, where the surfaces will be ground to their ultimate finish. The material leaves the heat treatment zone, transitioning into a calm stage for the next phase of processing. 100% of the steel rings undergo a transition to computer numerical control turning and grinding systems once the cooling process is fully complete. Why is such a transition to automated machining necessary after the initial shaping? At first glance, the forged rings appear finished, but in reality, they lack the micron-level accuracy required for high-speed rotation. Ultra-hard alloy cutting tools remove thin layers of metal to refine the diameter, thickness, and both faces of each component. This stage ensures every part aligns strictly with the specified design tolerances. It gets more complex further on. The equipment gradually grinds the raceway directly into the surface of the ring to create the precise track where the balls will travel. This internal path ultimately determines the smoothness and total service life of the finished bearing. One can notice how the grinding wheels move with absolute stability to maintain geometric control. Such precision is vital to preserve concentricity and minimize friction during future rotation. Transition to the next level. Ring surfaces undergo high-pressure shot blasting to remove stubborn oxide layers and any remaining microscopic burrs once the critical parameters are finalized. Millions of fine steel shots repeatedly impact the metal at high velocities. This process produces a more uniform and stable finish while simultaneously strengthening the surface through mechanical cold working. The reinforced metal becomes capable of withstanding repeated heavy loads in the most demanding operating environments. The equipment moves the rings to the assembly area where the bearing structure begins to reach its final completion. The inner ring is positioned slightly off-center relative to the outer ring to create a temporary opening. One can notice the polished steel balls being poured into a dedicated metal guide tube. From this tube, the balls slide along a slanted feed chute and drop sequentially into the raceway. The space between the two rings fills quickly as the balls occupy the circular channel. The ring assembly rotates slowly to allow the balls to distribute themselves evenly around the entire circumference. But this is just the beginning. A mechanical system simultaneously adjusts the internal alignment to ensure uniform spacing between the balls. This prevents any clustering that could generate unwanted vibration or heat during operation. The two rings are then returned to a perfectly concentric state, effectively locking the balls into their precise motion path. A cage is installed to maintain this structural order and prevent the balls from touching one another. The process is only gaining momentum. A layer of industrial oil or grease is added to the internal components to reduce friction and dissipate heat. This results in a fully assembled bearing ready to sustain smooth and reliable motion within modern mechanical systems. One can notice the thin film of lubricant coating the metallic surfaces as the unit is sealed. The journey of creating a bearing is a complex fusion of energy, heat treatment, and precision engineering. It spans from iron ore buried deep beneath the earth to components machined with micron-level tolerances. Metal is melted, shaped under immense pressure, and then refined so that the steel balls can move within a near-perfect structure. Small in size, these bearings form the fundamental foundation that allows countless machines to operate reliably every day. Raw materials are transformed through these stages into the pillars of the modern world. The transformation moves from raw ore to a finished mechanical assembly through a continuous industrial chain. From here, the finished components are prepared for distribution to various sectors of global industry. The journey concludes with the creation of a high-precision product ready for deployment. Thus ends the complex cycle of bearing production.